So welcome to this. This is the Further Math Support Programme online revision session for Edexcel Statistics 2. And in this session we're going to be looking at hypothesis testing. Now, hypothesis testing is pretty much the fundamental aspects of statistics. It allows us to make inferences as to whether a belief is true or not. So there's a variety of things you need to be able to do, and you need to be able to do them in a variety of different ways. So you need to be able to set up and actually perform hypothesis tests for either the parameter p of a binomial, and we're really looking for the word proportion here when we deal with this, and also we're asked to do a hypothesis test for lambda of a Poisson, which is we know as the rate, but they're generally asking for the mean. So if we can see that we're using a Poisson distribution, they generally ask you to test the mean, but I prefer to deal with lambda, and I'll show you that as we go through these. So you need to be able to perform a hypothesis test in two different ways. One of them is by using this thing called a critical region. You need to find them and use them. And basically, when you are doing these, the critical region is, as I'll describe in a minute, if your test statistic is in the critical region, that is quite significant. Also, you can do hypothesis tests by comparing your test statistic instead with something called a critical value, and I'll show you that on some later ones. You also need to understand when it's important to do a one-tailed test or a two-tailed test, because again that's going to affect your probabilities of what we call your significance level. So first of all, January 2010 question 6 starts off with a definition, and we're asked to define this thing called a critical region. And a critical region basically is the set of values for which your test statistic would lead you to reject your null hypothesis. So let's just formalize that. So it's the set of values. That's quite important. That's actually going to get you a mark. So it's the set of values for the test statistic, which is what comes from an experiment. So it's the set of values for the test statistic which leads us to reject the null hypothesis. And we'll talk about these hypotheses in a little while. Okay, so part B, it's going to start asking us to find the critical region. So they're guiding us through this question, which is really quite nice. So we're told that we've got a discrete random variable, so we don't need to define it, and it's going to have a binomial of 30p. Now we don't know what p is, which is why it's not been stated. A single observation is used to test, so this thing here is called your null hypothesis. So this is your belief. It's the belief that the proportion p is in fact 0.3. And we're going to test it against this thing called your alternative hypothesis, which is saying that p is not equal to 3. So this thing is basically saying that your proportion has changed, which is what makes this a two-tailed test. The other hypotheses you could have used is it's been decreased or it's been increased, and they are what we call one-tailed tests. Now we're asked to find this using a 1% level of significance. We're asked to state the probability of rejection in each tail. If you don't do that, you'll lose marks. And we need it to be as close to 0.005 as possible. Notice that's half of 1%. So we're splitting the 1% significance level in two because we're dealing with a two-tailed test. So it's worth 5 marks. So let's show you as we go along how we get these marks. So we've stated our null hypothesis that p is equal to 0.3. So we can now assume that p is equal to 0.3. So we're going to be dealing with the binomial 30, 0.3. And this is all pretty much going to be from your tables. Otherwise it's a bit hard work. So we're looking for what we call the critical region. So there's going to be a value, C1, which is going to lead me to be in the bottom 0.005%, and also we're looking for an upper critical value, which I'm going to call C2, which is going to be around about 0.005 as well. Now this inequality is pointing the wrong way, so I need to swap it around carefully because it's discrete. And with a little bit of rearranging, you can see that this is going to turn around to be roughly equal to 0.995. Okay, now the reason I do it this way, which is slightly different than the book, is that it enables you in my view, to use the tables a little bit more easily. So let's go back to this. What we do is we look for two probabilities that stagger 0.005, and they are when the probability of x is less than or equal to 3 and when the probability of x is less than or equal to 2. And from your tables, these have a value of 0.0093, and this one has a probability of 0.0021. And we can see that this one is closest to 0.005, which is what they're asking for. We do the same, looking for values that stagger 0.995. So that's going to be the probability of x being less than or equal to 15, and the probability of x being less than or equal to 16. So less than or equal to 15 is going to give me a value of 0.9936, and this one is going to give me a probability of 0.9979. And again, this one here is going to be closest. Now, just want to make a point. So here, this value is important, and this one. So this one is C1. This value is C2 minus 1. So C2 must equal 16. So your critical region is as follows. The probability of x being less than or equal to 2 has a probability of 0.0021. The probability of x being greater than or equal to 16 is actually going to have a probability of 0.0064. Okay, that's 1 minus this. And your critical region itself is going to be the union of x being less than or equal to 2 and x being greater than or equal to 16. Okay, so remind you where you get your marks. You get a mark for basically stating and using the binomial distribution. You then get 4 accuracy marks. So if you don't get this correct to start off with, you're going to get no marks at all. So you basically get 2 marks you get a mark for this accuracy, a mark for this one, and then a mark for each aspect of the critical region. So that's quite nice marked question. So we're then told to write down the actual significance. So this is the probability of being in the critical region. Now we've worked this out, we just need to add them together. So it's the probability of being either less than or equal to 2 or greater than or equal to 16. So you get the two probabilities, which is 0.0021, and you add it to the other probability of being greater than or equal to 16, and that gives us our probability. So 0.85% would be correct, or you could leave it as a decimal. You get 1 mark for that. We then carry out the experiment and we create this thing called a test statistic. So we've got to comment on this. So we can see clearly that the test statistic, which is 15, is not a member of the critical region. Now we've already defined that a critical region is an area where you would reject H0, so we're not in it. So in this particular case we do not reject. Some books use the word accept. I don't like that, so I'm going to not reject H0. Haven't finished, you need a sentence. So there is insufficient evidence to suggest that P has changed from 0.3. Okay, and we do need this statement. It's just good practice to do it. So that's 2 marks. You're going to get 1 mark for telling me that your test statistic of 15 is not in the critical region, and then you're going to get 1 mark for completing the statement. So this is a bit more. So that was quite a guiding question. This one's a bit more typical in terms of how it's presented, and we have to concentrate with these just to make sure we get things the correct way around. So Richard regularly travels to work on a ferry. Over a long period of time, he's found that the ferry is late on average twice a week. The company buys a new ferry to improve. We're looking at a 4-week period after the new ferry is launched, and Richard finds that the ferry now is late 3 times and claims the service has improved. And we're asked to assume that the number of times the ferry is late is Poisson. We're going to test at 5% whether this is the case or not. So first of all, we need to set up your hypotheses, and it says that we need to do that clearly. Now we're really testing the average. We're really testing the mean. So you could argue that this is what we're testing, which is entirely true. However, which way is this one? Improve. Therefore, the rate's got to go down. However, I want to use a Poisson, and just for convenience, I think that's better. So we're going to let x be number of lates in a 4-week period, and that leads me to lambda equaling 8, or lambda being less than 8. And I personally prefer to use these, okay, because x can now be assumed to be a Poisson 8, which is quite nice. Okay, so again, with this, we can then use the test statistic. So what I'm going to do in this particular question is I'm going to not look at critical regions. I'm going to do this in a subtly different way. And what I'm going to do is I'm going to look at the probability of being 3 or below. And I'll talk to you why I'm going to do this in a minute. So if I look at that, I can do that from my Poisson table. There we go, Poisson 8, 3 or below. So the probability of being my test statistic or lower is equal to 0.0424. Now why is this useful? Well, let's just draw some random graph just to show what's going on. So I'm basically stating that I have a value, and if I'm below it, then the probability of being below it is 0.0424. Well, that must tell me that this value here is in the bottom 5%, because there's only 4% of data below it. So therefore, 3 must be in the critical region. So because this is less than 5%, which is the level of significance I'm looking at, we actually reject H0 in this particular case. Okay, so there is sufficient evidence to state that the service has improved. Okay, so that's a different way of carrying out these test statistics. Instead of finding the critical region, which is very useful, you can also find the probability of being less than or greater than, depending on the direction of your alternate hypothesis. You can work out the probability of being below or above it. So again, you need to know where your marks are coming from here. So let's go back a page and just show you that. So you get 2 marks for getting your hypotheses correct, which is quite nice. You then get another mark, a method mark, for making the assumption. Okay, so x can be modelled as a Poisson 8. You only get 1 mark for working this out because it's just looking it up in a table. You then get a method mark for doing a comparison and rejecting H0, and you get an accuracy mark for making a statement. Now, if you didn't reject H0 and your statement was correct based on the fact that you've not rejected it, you will actually get a follow through there, just to make you aware, which is quite nice, really. Okay, so finally, June 2011, question 2. Traffic officer monitors the rate at which vehicles pass a fixed point on a motorway. When the rate exceeds 36 vehicles per minute, he must switch on some speed restrictions to improve traffic flow. The traffic officer records 12 vehicles, so there's your test statistic, passing the point in a 15-second interval. So again, we've got to make sure we're dealing with the correct aspect here. Okay. So the rate is 36 vehicles per minute. So either you're testing the fact that H0 mu is equal to 36. As I say, I, however, prefer lambda is equal to 9. You can only use that if you've defined x. So let x be number of vehicles passing in 15 seconds. Your alternate hypothesis is going to be, we want to see whether they should switch on the speed restrictions or not. So that's whether we exceed the rate. So either the mean is above 36 or lambda is above 9. So under the assumption, this is about rates, so it's going to be a Poisson. So it's going to be a Poisson 9. And again, this is why I prefer using lambda in my hypotheses. I'm going to do exactly the same thing. We've got a test statistic of 12. My alternate hypothesis is now pointing to the right, so I'm going to look at the probability that x is greater than or equal to 12. Okay, now that's kind of pointing the wrong way. So I'm going to change it so it's 1 minus the probability of x being less than or equal to 11. I can find this in my tables. So lambda is equal to 9, x is less than or equal to 11 is 0.8030. So the probability of x being less than or equal to 11 is equal to 0.8030. So the probability of x being greater than or equal to 12 is going to be 1 minus that, as we stated previously. So that's going to give me 0.197. So what this is claiming is there is roughly 20% of data above your test statistic. Therefore, you cannot be in the top 5%. That's the level of significance. Therefore, you are not in the critical region. So therefore, we do not reject H0. Okay, so there is insufficient evidence. To switch on the speed restrictions. Now you don't get the final mark in this if we don't mention this statement. Okay, so you must always make sure it gets contextualized back. So again, this is 6 marks and it pretty much follows the same pattern as previously. Let me change colors so you can see. So again, you're going to get 2 marks for getting the hypotheses correct. You're going to get 1 mark for doing this. You could do it using critical values as well, and there is mark schemes available for that, which is fine. You get an accuracy mark for working these out. Here, you then get a method mark for either rejecting or not rejecting, and then you get an A1 follow through again as before. Now, this is dependent usually on your hypotheses being correct. So if you haven't got your hypotheses correct, or the wrong way round, you generally don't get these last 2 marks either. So that emphasizes how important it is that your hypotheses are the correct way round at the start. So it continues. Traffic officer, same question. Using a 5% level of significance, determine the smallest number of vehicles the traffic officer must observe in 10 seconds. So again, you've got to have your wits about you because they've now changed the time frame again in order to have sufficient evidence. So this is really asking for something called the critical value. So it's on the way for finding a critical region. So let y be number of vehicles in 10 seconds. So that means that we can model this as a Poisson with a variable of 6 now. So if you look in your Poisson tables, we're looking for a critical value. So x is less than or equal to a specific critical value. Sorry, probability of x being greater than or equal to a specific value has got to be less than 5%. So again, we're looking at roughly 0.05. So just to remind you, this is pointing the wrong way, so we need to swap it round, which leads me to state that I'm looking for C2 minus 1 is around about 0.95. Now, I ideally want it to be less than 0.95, greater than 0.95. It's worth remembering this, by the way, just so you don't need to go through this derivation every single time. So the 2 values that stagger are these 2 here. So the probability of x being less than or equal to 9 is 0.9161. The probability of x being less than or equal to 10 is equal to 0.9574. And as I say, we're really looking for them to be less than, so that one will be greater than. So it's this one I'm dealing with here. So this tells me that C2 minus 1 is equal to 10. So therefore the critical value that I was looking for is 11. So we're going to need 11 vehicles before we have sufficient evidence to switch on the speed restrictions. Okay, so I've basically shown you three different aspects using two different distributions of how we can attack hypothesis tests. So again, it's important that you go through as many of these as possible. You may be asked to do approximations and then perform a hypothesis test, and that is laid out in one of the other presentations as well.